Hello, chemists. This is Miss Placino, and you are watching Screencast 9.5 on Hess's Law. In today's lesson, we're going to talk about how to evaluate multi-step reactions. That may sound kind of complicated at first, but Hess's Law really is less about chemistry and more about solving puzzles. So if you're somebody who's really into puzzles, Hess's Law can be a lot of fun. If you are somebody who hates puzzles, you'll come around, you'll warm up to it. Don't worry. So let's go ahead and get started. In a multi-step reaction, that really means that to get from initial reactants to final products, it's going to take multiple reactions. Probably not too much of a surprise. So we start with our reactants. And ultimately we'll get to our products. But unlike the potential energy diagrams that we've looked at so far, a multi-step reaction has like two hills in it, a little bit more of a roller coaster ride than the single-step reactions. And we're trying to find delta H for the entire process. I'm going to write the letter I here and the little valley. I guess that looks more like an H. Let's not do that. I'll just put a star there instead. So to get from reactants to the star and then to get from the star to the products takes multiple steps. So I've gone and I've calculated, or I've shown with this arrow, what I'm going to call delta H sub 1. And there's delta H sub 2. So I have products, or the star, minus the reactants to get delta H sub 1. And then I've got the products minus star to get delta H sub 2. I want to know the total delta H of the entire process. That's really from, final products to initial reactants, the subtraction. So I can add these two up. If you're looking at that and you're thinking, well, wait, no, I have to subtract them. Remember, the sign is going to be different. From reactants to the star, that's going to give us a positive delta H because that's endothermic. But from the star then over to the products, this is a negative delta H. That's going to be exothermic. That's something stubborn about writing. So my total delta H is going to be negative. So it's going to be delta H1 plus delta H2 gives you the delta H of the total process. We're not going to be using potential energy diagrams as we solve Hess's Law problems, but I just kind of wanted to show you what a multi-step reaction would look like. All right, this gentleman right here is Hess. Hess says that enthalpy is a state function. We'll talk about that in just a moment. But according to Hess's law, if a series of reactions are added together, the enthalpy change for the net reaction will be equal to the sum of the enthalpy change of the individual steps. So basically, the whole thing is equal to the summation of the parts, which initially might not sound like that big of a deal. But you got to remember, this was hundreds of years ago that this law was proposed. Let's talk a little bit more about a state function. Let's talk about altitude. And we're going to use our high school as an example. I know that you come in on the second floor. I don't know where you are the period before my class. And I know that ultimately, to get up to chemistry, you got to get up to the 9th floor. So you can go ahead and you can take the stairs. And you can get up to the 9th floor. We've got escalators. So maybe you're taking escalators. And you're able to get up close to the 9th floor, and then you have to take the stairs because it's just odds and evens are connected. Let's get rid of that. Maybe you were able to sneak on the elevator and you were able to go up. Or maybe you started to sneak on the elevator, a teacher caught you and then brought you back down to 1, and then you had to take the stairs all the way back up. Regardless of your story, how you get from the 2nd to the 9th floor is irrelevant. You're going to be covering the same altitude. It doesn't matter if you take the stairs, the elevator, the escalator, or some combination of the three, your altitude change is the same because altitude is a state function. That means it is independent of path. It does not matter how you got from point A to point B. Regardless of the mode of getting there, the distance, or I should say the altitude traveled, is the same. Let's compare that to distance. Right now I'm teaching in room 940, and the bathrooms are over here. Now I know some of you, when you ask to go to the bathroom, you're very, very, quick about it. Just you go and then you come back. I know some of you are not, and you leave class and you walk over the other side of the hall to see what's going on in the other class, and then you're wandering and you go make faces at your friend, and then you go to the water fountain, and then you go to come back. Oh, wait, I'm going to go to the bathroom. I forgot. Okay, and then I come back and get more water and see my friends again, and then finally I come back to class. Whew. Distance is not a state function. Distance is dependent upon path. If you take a very direct route from the classroom to the bathroom, you're going to walk a much shorter distance than somebody who wanders around, going to the water fountain, forgetting what they're doing, trying to say hi to their friends in other classes. Distance depends on path. So what Hess is telling us is that enthalpy behaves a lot more like altitude. It doesn't matter really what type of reactions occur, whether they're exothermic or endothermic. You can figure out the overall enthalpy change if you look at where did I start and where did I end up. If enthalpy was more like distance, we would not be able to do this. The reactions that occur would really dictate what the overall enthalpy change would be. So this is why we are able to apply Hess's law and figure out the change in enthalpy for a multi-step system. No, I'm never going to be able to read that. So let's do an example with Hess's law. So we're going to try to use the following equations to determine the change in enthalpy of this reaction. We've got methane reacting with oxygen to form carbon dioxide and water, a combustion reaction. And here are the three that we have. So we know that carbon plus oxygen makes CO2. And we've got this delta H value. We've got the formation of water and its delta H value. And we have the formation of methane and its delta H value. And we're going to try to manipulate these three steps or these three reactions so that we can get an overall reaction of that. And this is where the part of Hess's law being more like a puzzle is going to come into play. It dawned on me that it would probably be easier to walk through this problem in your workbook than just on my PowerPoint, so I switched over to the workbook. Okay, so here's what we need to do. Basically, you want to size up these three intermediate reactions and try to get the substances, for example, carbon, oxygen, carbon dioxide, so that they're on the correct side of the goal equation. So a lot of times I'll call these three over here like my given equations, and then the equation that I'm trying to make I'll call my goal equation. And what you want to do, again, is get the substances that show up in the goal equation on the right side of the arrow for each of the intermediate equations. And if you've got things that don't show up in your goal equation, you want to try to get them to cancel out. And the way something's going to cancel out is that it shows up on both the reactants and the product side. And therefore, if it's both a reactant and a product, it's an intermediate, and it can get just crossed out. So let's work on this together. Think about thought process. Get rid of all that extra writing. Okay, so I'm going to look at equation number 1 first. I have carbon, oxygen, and carbon dioxide. So I'm going to take a look at my goal equation. Do I see carbon, oxygen, or carbon dioxide? Yeah, I do. I've got oxygen and I've got carbon dioxide. Oxygen is a reactant, carbon dioxide is a product. Let's check the intermediate equation. Oh, perfect. Oxygen is a reactant, carbon dioxide is a product. So I can probably get away with not doing anything to this first equation. I can leave it exactly the way it is. If I change anything around, I'm going to mess up what side the products and reactants are on. So equation 1 can be left alone. And I'm just going to rewrite it over here. And I'm going to be lazy and leave out my phases. So I've got carbon plus oxygen makes CO2. And delta H is going to stay exactly the same at negative 393.5. And I'm going to ignore kilojoules right now because I'm a little bit tight on space. All right, let's look at equation 2 since we've taken care of equation 1. I say I have hydrogen, I got more oxygen gas, and I got water. If I go back to my goal equation, well, oxygen, I know it's on the reactant side. Good, it's over there on the reactant side. Water's on the product side. Oh, cool, water's on the product side over here. I have 1 mole of water, I should say, in my given equation. I need 2 moles of water in my goal equation. If you take equation 2 and you multiply it by 2, multiplied by 2, or doubled. So let's do that with the equation first. So that gives me 2H2 plus O2 is going to make 2H2O. And since I've doubled everything or multiplied by 2 in my chemical equation, I also have to do the same thing to my delta H value. So delta H in this case would be equal to negative 571.6. Again, I'm going to leave off kilojoules in the interest of space. All right, question number 3. I've got carbon, hydrogen, and methane. Carbon and hydrogen don't show up in my goal equation anywhere, but methane does. It is a reactant. And the given equation, methane is a product. So I'm going to need to flip that around. Oops. Sorry about that. So I'm going to take CH4. You're really going to want to make sure that your reaction arrows stay lined up. It's going to help you keep things organized. Is equal to C plus 2H2. So in equation 3 should be reversed, because CH4 is a reactant, and in the desired equation, or the goal equation, therefore the sign of delta H should be flipped. So the number itself does not change, flipped, but the sign does. So I have positive 74.3 kilojoules. Okay. Now everything is in the right place, hopefully. So I need to add these reactions together. I'm going to use blue to cancel stuff out. If you have a substance that is a reactant in one of the intermediate or the given equations, and it is a product in another, it can cancel out. For example, I have carbon in the first equation as a reactant and carbon in the third equation as a product. So that means that they cancel. Is there anything else present that I can cancel? Yeah, there is. I've got 2H2 on both the reactants and the product sides, so those will cancel out. There's nothing else for me to cancel, so I'm going to add them together. So the H2, more specifically the 2H2 and the C, are able to cancel out. And we're going to add everything else together. So I've got CH4 plus O2 plus O2. So let's make that 2O2 makes CO2 plus, oops, 2. Goodness, sorry, I'm making a mess. Plus 2H2O. So I've added my equations together. I'm going to do the same thing with delta H, add that together, and I end up with about negative 890.8 kilojoules. I'm going to finish this up. We add these together, and we end up with a final enthalpy of negative 890.8-ish kilojoules. And if you were to go back and look at table I, the combustion of methane is provided there, and you end up with basically the same exact number. I think we might have a different digit in the tens place, but probably caused by rounding and stuff like that. So what this is trying to show you, or what I'm trying to show you, is it doesn't really matter how you get from point A to point B when it comes to enthalpy. The overall change, if we go from reactants to products, can be figured out simply by adding up the delta H changes for all the intermediate steps. And that's how Hess's law works. So I'm going to go through one more problem with you just to make sure that you got the hang of this, but really the best way to get better at Hess's law is, as with the overwhelming majority of the chemistry stuff that we do, is through practice. So let's say that you have this information. You've got the synthesis of nitrogen dioxide, and you have, it's called dimerization. It's kind of another synthesis of dinitrogen tetroxide. And you want to find the enthalpy change of this, taking dinitrogen tetroxide and decomposing it into its elements, N2 and 2O2. Now this one is hopefully a lot simpler than the one that we just did. If you could follow what was going on with that previous problem, then this probably is going to be a walk in the park for you. So what you want to do, as with the last problem, is to try to set up your known or your given reactions so that the unwanted species, whether they're compounds or elements, cancel out. You have to have the same species as a reactant in a product to cancel them. And you add the two reactions together and get their delta H values. So I have the synthesis of nitrogen dioxide, and I've got nitrogen dioxide, two of them joining together to form dinitrogen tetroxide. So if I looked at my goal equation, I know that it's this NO2 term that I don't want to stick around. I got to get it to cancel out, so I put it on the reactant side and on the product side. They cancel. I can add up the remaining reactions and calculate the delta H value. Here's a tip. You don't want to try to add reactions until the very end. You don't want to, if you have 3 reactions or 4 reactions that you're playing around with, try to add just a couple at a time. You really need to make sure that you have all of the reactions dealt with, so you've either flip them if they needed to be flipped, or multiply them to get the correct coefficients before you start adding. If you try to do it incrementally, you are going to be dead in the water. You'll screw it up every single time. It never ever works that way unless you get really lucky. If you switch the direction of the reaction, you need to switch the sign of delta H. So we had the synthesis of N2O4. In reality, we want the decomposition of N2O4. So we switched the direction, so the numerical value of delta H stays the same, but the sign changes. There are going to be times where you're going to have to multiply or divide to get the correct coefficients. So you do the same thing to delta H. For example, if all of these were doubled, 2, 2, and 4, and we wanted to get back to just the lowest possible coefficients, I know that I'd have to divide this by 2, so I'd also divide delta H by 2, and that's how I'd get it figured out. Okay, again, practice problems are really your best bet here. Keep going through the procedure and the process. Make sure you understand what's going on. I said it at the beginning, I'll say it again. Hess's law is less about chemistry, and it's really more a puzzle. It's about getting those compounds or elements that you don't need to get in positions where they can be canceled. Once things can cancel out, you can get rid of kind of all the noise, and you can get it down to just the compounds or elements, the chemical species that you're interested in. Add up delta H at the end. Keep in mind, whatever you do to an equation, you have to do to delta H. If you multiply the coefficients by 3, delta H better be multiplied by 3. If you change the direction of a reaction, you need to flip the sign of delta H. And if you keep those couple of rules in mind, you're going to see that Hess's law problems can actually be kind of fun. All right, as always, check the answer key as you're solving the practice problems, and this is another topic we're going to dedicate some more time in class just to let you practice and reinforce it. Thank you for tuning in, and I hope you found this helpful.